Welcome back and thanks for joining us again here at our live webcast celebrating ESO's 50th anniversary. So earlier in the webcast, we asked you another quiz question, giving you another chance to win a copy of our 50th anniversary coffee table book, the DVD and Blu-ray. So the question was, arrange the ESO sites in increasing order of altitude above sea level. And the correct answer is, of course, La Silla at 2,400 meters, Paranal at 2,600 meters, Armazones at 3,060 meters, and then, of course, Chajnantor with 5,000 meters, by far our highest site. And the lucky winner is... Where is he? Where's he gone? Pavel Pech from the Czech Republic. So, congratulations. Well done. The next question, moving straight on. Again, we have, today is not only the ESO's 50th anniversary, but there is another 50th anniversary today, and that is one of the birthday of one of the most famous Beatles songs, Love Me Do. Now the question is, which of the following songs is also by the Beatles? Is it A, Susie in the Sky with Diamonds, B, Moonlight Coast, C, Across the Universe, or D, Mrs. Moonlight? Get it right, and you too could win the beautifully illustrated coffee table book, Europe to the Stars, Exploring the Southern Skies, ESO's first 50 years exploring the southern skies. And of course, along with that comes the DVD, the movie version of the book on DVD or Blu-ray. And of course, you can enter online at the URL that is on the screen right now at bit.ly/ESO50quiz7, bit.ly/ESO50quiz7. Stay tuned. Later on, we'll be revealing the answer and the winner, of course. But now it's time to move on to the next in our series of talks from astronomers and engineers here at ESO headquarters in Germany. And the next speaker, it's a pleasure for me to introduce him. It's Dietrich Baade. He's an astronomer here at ESO. He's the head of our instrumentation science department, and he will be telling us about planets and planetary systems. However, before I let him start, just a quick reminder, you can send us your questions and comments via Facebook, Twitter, and email. So now, please welcome Dr. Dietrich Baade.
Yeah, thank you very much, Joe. And dear friends and guests of ESO, those of you who had a chance to see the previous episode of our Jubilee movie will know already that there are planets beyond the solar system and that they orbit other stars. Now, we are still very deep in the process of digesting all the information that is flowing into our computers. And one of the lessons that we have learned already is that every planet must be understood in the context of its local environment. And perhaps to make this plausible, one could use the following comparison. Just imagine that some aliens have spotted a football player and are studying that person very carefully in all detail. But they're studying only this one person and nothing else. And would they ever have a chance to understand what football is about? No, of course they wouldn't, because football is meant for teams, and they would never see that. And therefore, the conclusion is that it is very important that one does not study just one player, but a whole team. And by analogy, in our case, one does not study just one planet, but a whole ensemble of planets, a whole planetary system. And then, by the same logic, it is of course also clear that it is not sufficient to study just one team. One cannot understand the solar system by just observing the solar system itself. You must compare it to other planetary systems. And so therefore I would like to invite you on a little virtual tour which will take us to some extrasolar planetary systems, back to the solar system. And we will be driven by the question whether from the comparison of the two, we will get a clue as to our origins. And it's very early days for that question, but we are laying the foundation to its answer. And it's perhaps also very appropriate to talk about this subject here and today, because this very new territory has been charted to a large extent also with the help of telescopes at ESO. So just as a reminder, we can ask ourselves, what are the main characteristics, the top-level characteristics that describe the solar system? And of course, there's one central star, namely our sun. And there are many planets, namely 8. Now, we have seen many of the pictures like the ones that I'm showing here, and they all say they're not to scale, and this is not so because people cannot imagine anything else. It is just so that the dimensions of the solar system are so big that you cannot image them all to scale and depict the planets at the same scale as the distances between them, because the space of the solar system is so empty. Sometimes, though, it is still possible from the ground to see a fair fraction of the bodies of the solar system. And just last year, we had such an occasion where you could see with the naked eye 6 solar system bodies at once. And if we now go to extrasolar systems, today about 660 stars are known to host at least one planet, and 20% of them have already been detected to host at least a second one. So there is already the basis for the comparison that we want to do, and these comparisons promise to be quite exciting. So we start with one of the first such multiple planet systems that have been discovered and was discovered at ESO. There have been dubbed the 3 Neptunes because with masses between 10 and 18 Earth masses, these planets have a mass that is very comparable to the 17 Earth masses of the Neptune in our own solar system. So that comparison is quite appropriate. However, if you look at the orbital periods of the planets, then for the 3 Neptunes, they're of the order of just a few weeks, whereas in the solar Neptune, the period is 165 years. That's a difference by a factor of 1,000. And when you look at the radii of these orbits, the difference is still a factor of 100. So that must be a very different breed of planetary system. Another very interesting, very exciting example is Kepler-47 that was discovered by the Kepler satellite, the Kepler spacecraft. And when you look at the green rings, these are the zones in which there can be liquid water at the surface of a planet. And that is, of course, a necessary requirement for terrestrial life. Now, in Kepler-47, you see that in that green belt there is one planet, namely Kepler-47c, but it is very much larger than the Earth, and so we are not sure whether it's a rocky planet which has a solid surface or whether it's a gaseous giant. But this system is still much more remarkable for the fact that it has actually 2 central stars. There are 2 suns at the center, and until the discovery of this system, I think very few astronomers would ever have bet that one would find such a system. So if we now return to the solar system and have a closer look at it, then we see that the planets are only the tips of the iceberg. We have the sun at the center, and it is orbited by the major planets, and interspersed with the major planets are the minor planets. They mostly cluster in the asteroid belt, which is between Mars and Jupiter. And we have similar bodies much farther out in the solar system. They populate the trans-Neptunian region beyond the orbit of Neptune, and they are called the Kuiper belt. Still farther out, and no longer confined to the disk, to the plane of the solar system, but filling a sphere, are the comets, and they form the so-called Oort cloud. This fits quite well what today we believe we know about the formation of stars and planetary systems. And it all begins with the collapse of a cloud of gas and dust in the interstellar space. In this medium, the dust grains coagulate to form planetesimals. And then the power engine in the, at the same time, forming star starts to work. It's powered up. It radiates a lot, and this radiation pressure drives away all the gas and all the dust that has not been used for the formation of planetesimals. And what we are left with are myriads of pieces of gas and dust as kind of interplanetary debris. The planets continue to grow, and after a while we have the planetary system fully developed. Just to give you an idea what the comets look like, here are 2 pictures. The comets are mostly icy bodies with a diameter of a few kilometers. By contrast, the asteroids can be very much larger, up to several hundred kilometers in diameter, but down to meter size. And their composition is different because they mostly consist of rocky material. Altogether, the planets, the minor planets and the comets do not make up more than 1/1000th of the mass of the Sun. And if you put them all together, their diameter would not be larger than, say, 1/2 of the diameter of the Moon. So that's not too impressive, and one would not feel threatened by it. But they are still not without risk. On the contrary, they have posed very high risks, which have also materialized on Earth and elsewhere, because their small mass makes them very vulnerable to attacks, to kicks by other planets or passing stars. And if they get then close to the Earth, which has a much stronger gravitational pull than they have, Earth may actually divert them so that they hit the surface of the Earth, which is very dangerous. And today we believe that, for instance, the dinosaurs became extinct because of such an impact event. And when you look at other bodies in the solar system, where there is no erosion due to rain and wind, you see that they're full of scars of impacts on their surface. Actually, only 20 years ago, we have had the possibility to follow such an event in real life. When a comet first goes very close to Jupiter, broke up under the influence of the gravitational field of Jupiter, returned to Jupiter, and then one piece after the other hit the surface of Jupiter. This is actually a minority event. Most of the such bodies that approach Jupiter would not hit the surface, but would be diverted. And that is the contribution that Jupiter has made to the evolution of the solar system, because it has ejected most of the asteroids and the comets from the inner solar system, so that today this inner solar system is fairly empty, even though it's not clean, because otherwise we would not see, for instance, meteor showers. So there's still some matter in that area, which also from time to time gets close to Earth. So against all this evidence that there are some motions, we have to ask ourselves, how stationary is the solar system? Of course, all the bodies orbit the Sun, but are these orbits stable all the time, or do they change with time? And obviously, the comets did not form where we see them today, because they're in the spherical structure of the Oort cloud. The asteroids are not evenly distributed in the disk of the solar system, but they cluster in two belts, the Kuiper belt and the asteroid belt. And most of the impact craters that we see on the surface of solar system bodies are rather old, which means that the ammunition has vanished quite a while ago. From laser lunar ranging experiments, we know that the Moon is moving away from the Earth. We also know that the planets interact with each other, and for instance, this has enabled the historical discovery of Neptune through the effect that it has on the orbit of Uranus. And so this then leads to the question whether the planets remain where they have formed. And we cannot answer that question on the basis of observations of the solar system. We have to go to extrasolar planetary systems, and the answer will come in two installments. The one is less complete, but also less violent. And of course, Jupiter must have moved slightly inwards, because it has kicked out all the comets and asteroids. And so to compensate for that, the loss of energy had moved closer into the Sun. Now, the general question is, of course, how does a planet know after its formation where it should settle? Probably it doesn't get a ticket like in a movie theater with a number of the row and a number of the seat. And so we have to look at other planetary systems to see in what structure, in what state we find them. And here in this diagram, you'll find in every row one star. The name of the star is on the left-hand side. And the stars are sorted by the mean mass of the planets, with a low mass at the top and the heavy weights at the bottom. And on the horizontal axis, you see the separation of the planets from their host star. And every planet in a given solar system is represented by a spot, and the diameter of the spot tells you how big or how massive the star is. And you see the solar system marked with the Earth and Jupiter. And you can also identify our three friends, the Neptunes. And you see again that this is a very different type of planetary system. But the real excitement in that diagram lies in its lower left corner, where we have big spots. So these are Jupiter-sized planets, but they're up to 100 times closer to their central stars than Jupiter is. So that means that they receive an amount of radiation that is several thousand times as large as the one that Jupiter receives from our Sun, and therefore they are dubbed hot Jupiters. And there have been a big puzzle because it was clear that hot Jupiters cannot form where we observe them. They cannot form so close to the central star. And the only conclusion is that they must have migrated inwards, probably as a result of the drag of the gas that is still in the disk in the early phase of the formation of these planets. And so we then come to the second part of the answer, the more important one, and also the more violent one. We see that systems with hot Jupiters are very deficient of other planets in the inner system. And, well, it's not quite as bad as cannibalism, but you will ask yourself, is it planetary bowling? And yes, it is, absolutely, because Jupiter has a mass which is 300 times the one of the Earth. And if two such planets get close to each other, it's clear who is a loser, namely the rocky planet. And if this had happened to Earth, we would not be here. The Earth would have been kicked out far away into the outer solar system, or might have fallen into the Sun. At least there would be no life. We would not be here. Still, the Earth in its youth had a somewhat adventurous life, because when it was only 1% of its age today, it was hit by a planet which probably had the size and the mass of Mars. And this led to the ejection of matter, the spawning off of matter, which then settled in the form of the moon, which we can still see today. Now, early astronomy earned itself a reputation for being able to predict the motions of planets very precisely. And one, of course, has to keep in mind that the time spans for these predictions were just a human generation or a few, and not billions of years. But then you could still say, oh, wait a minute. Since you have this precision, why can't you let the clock time and the computer run backwards and therefore just reconstruct what has happened? And so you flip this over and let the planets run backwards, and the computer is quite happy to do that. Unfortunately, this doesn't work because planetary systems are not clockworks. And they're not clockworks because bodies may leave, such as a planetary system may have left the solar system. Bodies may have collided with each other, and there may also have been close encounters with other stars passing the solar system during the billions of years of the existence of the solar system. And we are sure that such events have taken place, but we do not know when and under what circumstances. And therefore, we cannot feed the necessary information into our calculations. And we cannot calculate the history of the solar system back over more than 0.2 billion years. Now, if you compare this to the age of the solar system of 4.6 billion years, this means you can only go back in time for the last 5% of the age of the solar system at most. And what we are really interested in, where most of the action was, were the first 10 or maybe 20%, so we lose on the whole front. And it will be necessary if we observe extrasolar planetary systems in order to understand our own home, and we will need the ERT for such observations. And so we have a first lesson that we can derive for our solar system from exoplanets, namely that the solar system is by no means typical of planet systems, and many extrasolar planetary systems, for instance, differ by the presence of a hot Jupiter, which probably has eliminated quite a few of the inner rocky planets. And this also means that the scope of astronomy is changing. So far it has been one-directional mainly, namely we have been taking the physics, the laws of physics that we have recognized and understood here on Earth in the solar system, have projected them far away in space and time, and have verified that they're still valid there. That was perhaps one of the biggest triumphs, the intellectual triumphs of humanity. Now, the additional thing that astronomy does is that it imports insights that are collected from extrasolar planet systems in order to understand the genesis of our own solar system, and of course, ultimately, to understand the genesis of terrestrial life. And this story is still a very young one. Actually, tomorrow will be the 17th anniversary of the announcement of the first unambiguous detection of an extrasolar planet. And so we can be sure that this story will continue, and I'm sure that you can find the continuation, further chapters, on our web pages. So please visit us from time to time. Thank you.
Thank you very much, Dietrich, for that wonderful presentation about planets and planetary systems. That was great insight. Thanks very much. So I have quite a lot of questions, actually, for you. Your talk generated a lot of interest amongst our viewers. So let me start off with this question here from Malcolm McKellar in Port Douglas in Australia. And he asks, so given the extent of telescopic exploration of exoplanets and the discovery of numerous exoplanets, as well as all the successful detections of many solar system bodies and many moons around planets in our own solar system, so why do you think it is that we have not yet been able to identify any signs of extraterrestrial life, except for some tenuous signs of methane of oxygen in some exoplanet atmospheres?
Well, it's a very tall order, and it was explained by some of the previous speakers. It takes an ELT to just get an image of such a planet. Image means that you fill 1 pixel with the light of it. You don't see any structure on it. You don't see the shape of the planet, no nothing, no clouds. And when you project this onto an instrument in the ELT, you have a separation between the star and the planet of the order of 0.5 millimeter. And the contrast in the brightness will be 10 billion. So that is not easy. It is not possible with current equipment. And the reason why you want to have that picture, it's of course good for PR work, but for practical reasons, you need it in order to take a separate spectrum of that planet. And only when you have a spectrum can you tell whether, for instance, you find signatures of chlorophyll, right. And only then can you be somewhat confident that you find life that is similar to our terrestrial life. If they're completely different forms of life, that will be another puzzle.
I guess the question was also a little bit about why do you think it is that life seems to be relatively rare. So in the solar system, despite some intensive searches, we haven't found anything yet.
In the solar system, well, we are only beginning to explore that, and you will have heard about the recent discovery of strong evidence of significant amounts of liquid running water on Mars. There are some moons which have liquid interiors, and they are heated by the radioactive decay of radioactive elements. So they might also provide an environment for life. So I think we should be cautious. The question has not yet been answered. Okay. We are just starting to ask it.
So there's a question from Matthew Dullenkopf via Facebook, and he's asking a little bit about the origins of our own asteroid belt in the solar system. So he says our own asteroid belt seems like there should have been a planet there. Was there a planet there which was destroyed later, or what's the origin, or what is the asteroid belt?
First of all, the asteroid belt is an artifact because the inner part of the asteroid belt has been cleared by Jupiter and the interaction. So we cannot really reconstruct exactly what the state was, and that is one of the reasons why we want to study extrasolar planetary systems for comparison. And of course, the asteroid belt is at the boundary between the rocky planets and the gaseous planets. So it may also be that this is just the interface between different physical conditions.
Mm-hmm.
The total mass of these asteroids is very much smaller than any one of the planets. So it's not so that one planet was blown apart and these are the remnants.
Right. So that's not, exactly. So a question from JT via live stream. Have there been any exoplanets discovered in triple star systems?
Not to my knowledge. And as I said, no one would have bet any significant amount on a binary system to be the center of a planetary system.
Yeah.
There are significant problems with stability.
Mm-hmm. A really good question from Space Bats via live stream. Was it expected from theory that other stars have planets, or did the discovery of exoplanets give rise to a completely new theory, or to a better understanding of the formation of planetary systems?
I think we had some idea before exoplanets were discovered how the solar system formed, and it would have been very courageous to assume that we are unique. And that has already been shown after Kepler, etc. So it was just so that people thought it's very difficult to detect them.
Mm-hmm. So I have a light-hearted question for you from Corinna Wales via live stream. Have we ever observed any unidentified flying objects at the ESO observatories?
Yes, there was one, and that was during the old days when one would observe with an open dome, not in a computer control room, etc. And there was some funny structure, ring-like structure, and one of my neighbors in a neighboring telescope told me that he saw something brightening up and some bow shock, etc. And that, of course, was all very exciting, very entertaining, and we guessed right. This was, I think, a meteorological rocket or so, and the second stage it was ignited. Right. So it was unidentified at the beginning, but we could identify it.
Later, okay. So we now have a question here from Denis Zenko via live stream. How many solar system planets will survive after the Sun goes through its red giant phase before becoming a white dwarf?
Well, the Sun will expand to at least engulf the orbit of the Sun, and it may still severely affect Mars. And then there's a somewhat larger gap. Jupiter is at 5 astronomical units. It should be relatively safe, but it has a gaseous surface, so it will heat up, will also change.
Right. So a question from Fabian Reimann via live stream. So if we look at a star that is 20 light years away and would detect an exoplanet, wouldn't we see the planet like it was 20 years ago?
Yes.
Exactly.
But the Earth doesn't change in 20 years, so it doesn't make a big practical difference, I believe.
Right.
Unless there are humans there or something like that who are not peaceful.
There's a question from Ignacio Tares here via live stream. I think we had a similar question earlier in the day, actually. After finding biological activity signs in an exoplanet's atmosphere, what do you think will be the next step? So what will we do next?
I think one of the next steps is perhaps to search for radio signals. And if we have antennae that are significantly sensitive and they can be focused on this one spot and we see radio traffic, then we know that there must be some intelligent life. And then one could also try to beam up some messages, but that would take 20 years to go, then 20 years to come back. So it's not a very entertaining exchange, but an exciting one.
So I've got several questions here about the ELT and the role that the ELT will play in this science area. So I have a question here from Fabian Reimann again about, oops, no, it just moved. Could the ELT find a possible exoplanet around Alpha Centauri?
Yes, of course. Alpha Centauri is the most nearby star, so that in principle, technically, is the easiest case. Alpha Centauri is a binary, so that may be a mechanical challenge whether such a system is stable enough, but yes.
The other ELT question I just had, oh, there it is. So, what happened? It just moved. Will the ELT be able to analyze and find life from spectroscopy into of other planets? This was from Constantine. Sorry, can't pronounce the last name via live stream.
Yeah. That, of course, depends on how far the stellar system is, the host star, how big the separation is. But that's, of course, one of the top-level objectives that one can take a spectrum.
Yep, that's the idea. That's right. From Kuba Boczynski via live stream, could ESO contribute to the search for exomoons?
Exomoons are something very exciting. I have only touched on this with the story about the formation of the moon. We don't know really for sure how important the moon is for life on Earth. So that's an exciting thing. But first things first, so I think we are happy once we have found an Earth-like planet. The moon only has 1% of the mass of the Earth.
There's another really good question from Philippe Cornet via live stream. So, could exoplanets form around very massive stars, or would the strong stellar wind prevent the accretion of dust in a protoplanetary disk?
I think they could form at a larger distance, where then the effect of the radiation pressure is smaller. But the lifetime of these massive stars is very much shorter. They burn up their nuclear fuel so quickly that their lifetime is just a few million years, and maybe the planets are not even ready before they get destroyed.
Okay, so I believe that is pretty much all of the ones that I have. Have I just checking whether I've overlooked something? Oh yeah, there was actually another one. Another one from Matthew Downkop via Facebook. I think this is the last question I have now. So if a gas giant exoplanet were thrown out of orbit and traveled into a nebula, could it create a new star?
I think that question has not yet been discussed in the literature. If it would act like a condensation nucleus as a dust grain for the formation of a raindrop, maybe, but I think that comparison would be rather far-fetched. Right. Would be my spontaneous answer.
Yeah. Okay. Thank you very much, Dietrich. Thanks for joining us here at the webcast, and thank you for a very interesting presentation. Thanks.
Thank you. It was my pleasure, and thanks for all the nice questions.
Okay, so what's up next? So when we come back, by now, it is now pretty late in the morning already in Chile, and by now the sun is well and truly up at the Paranal Observatory. So when we come back, we will be returning to our flagship observing site at Cerro Paranal, the home of the VLT in the Chilean Atacama Desert. So we'll reconnect up there, and we'll make a live video link to the observing platform that is right the outdoor mountaintop itself, right outside the VLT. So from there, we'll be talking to one of the astronomers there, working the day shift, and of course, we'll find out more about how our lucky competition winner, Brigitte Bailleul, is enjoying her trip. And then, finally, as promised earlier, we'll also bring you the results of the processing of the observations of the Thor's Helmet Nebula that you saw the observations taking place right at the start of this webcast. So we'll be showing you the full color image shortly.